Okay. Thank you very much for inviting me here. Thank you. Um, so yes, I will say something about Diophantine geometry and O-minimality, which is something I've been working on for the last 10 years. And so this is a subject which is started in the UK by Jonathan Peeler in Oxford. Well, he worked with other people in other countries, but it's really he was the first, along with Zanye from Pisa, to apply O-minimality. I will say what it is briefly later, but it's something coming from model theory, from logic, even though it's also related to the ideas of Grothendieck, so-called tame topologies. I'll say a few words about it. So, so this is a very active area. There are people in the UK, namely in Oxford, Reading, London, Warwick, Manchester, working on it. Also collaborating with people in many countries, France, Italy, Germany, Israel, Canada, US, etc. So, well, let's start. So Diophantine geometry is simply the study of equations of the form f of x1, xn equals 0, where f is a polynomial, well, say traditionally with integer coefficients, although you can look at polynomials with coefficients in number fields or rings of integers of number fields. And so given a system of such equations, you want to know something about the integer rational solutions to this system of equations, and questions like, are there infinitely many? Can you find any of them? And the most famous example is of course Fermat's last theorem, which is the fact that the equation x to the power n plus y to the power n equals z to the power n has no non-trivial solutions when n is bigger than 2. And so now well, this statement that already has been mentioned in the previous talk is I think is the most general statement in Diophantine geometry known so far. So this is a famous theorem of Falting's, well, previously known as Mordell's conjecture, although now there are, I think, 3 proofs of it, quite different. And one uses some of the latest one by Venkatesh and Lawrence, uses, I think, some ideas of minimality and other things. So this the statement is, if you take a curve of genus G, of genus bigger than 2, defined over a number field K, then for any extension finite L of K, the set of rational points over L is finite. So this is quite a remarkable statement in many ways. Well, first of all, for example, as far as I know, before it was proven in '83 by Faltings, there wasn't a single known example of a curve of genus bigger than 2 who has the property that has finitely many points over any finite extension. And Faltings proved it indirectly. He proved theorems about Galois representations of abelian varieties, which in themselves are extremely important. This statement in 1983 and received the Fields Medal for it. So another feature of this this theorem is the fact that the genus is something which is geometric. So a curve of complex numbers looks like this. It looks like a connected sum of a certain number of tori, or a sphere with a certain number of handles, and the number of tori is the genus. So here is 3. And so it's the geometry of the curve that determines its arithmetic property, the existence of finiteness of the set of rational points And they're far-reaching. So this is a general philosophy started by, I think, Serge Lang. The geometry of an algebraic variety should determine arithmetic. And there are higher dimensional analogs of generalizations of these statements. This statement, which are, I think, still largely open. And this is also an active area of research. But so why I'm mentioning this, this is because this is actually related to the sort of problems I will talk about. And the direct approach to this is like this. So let's assume, to simplify, that K and L are rational numbers. And suppose that C has a point over Q. Well, then you can embed C into its Jacobian, which is an abelian variety. So this is a high dimensional generalization of elliptic curves. Well, in such a way that the rational points of C are exactly the intersections of C with the rational points of the abelian Jacobian. And, well, as mentioned in the previous talk, this model Weyl theorem, which says that this group, A of Q, is a group, is finitely generated. And so the question, I mean, the Falting's theorem model's conjecture will follow from the following statement, that a curve in an abelian variety intersecting a finitely generated group in infinitely many points, well, it should have genus 1. It should be a translate of an elliptic curve. And this is, in fact, the sort of statements that where O-minimal strategy applies. So there's a far-reaching generalization of it, which is model line conjecture. And here, so you take a finitely generated group, and instead of intersecting a variety with the group, you intersect with this larger set, which is the set of points such as some multiple belongs to this finitely generated group. Now, if you take, for example, a group to be the trivial one, 0, then you get exactly a set of torsion points. And the conclusion is that if you have a subvariety which intersects, whose intersection with the set I defined here for some finitely generated gamma is Zariski dense in Z, which means that it's not contained in any proper algebraic subset, then it should be a translate of a subgroup of A by an element of this set, of course. And yes, as I said, if you take 0, so this set are just torsion points, and then you get what is called the Mannion-Mumford conjecture, which is proven. This, in fact, was the starting point of this O-minimal strategy. Hila and Zanya proved it using O-minimality, and in 2006, I think. And but this statement has lots of genuinely different proofs. The first one was due to Michel Renaud using p-adic techniques, but there are many others. And O-minimal one is one of them. So so this model line conjecture is a theorem which should be attributed to a number of people. I list here Falting's, Andrei, McWillan, who is Scottish actually, Renaud, Voiter. There's also a multiplicative analog of it. So for subvarieties of the torus. And this is due to Laurent in 84. So before, about 10 years before model line conjecture was proven. Yes, so this is exactly the sort of questions. So this implies models conjecture in particular. And this is exactly the sort of questions that we'll look at. So what is O-minimality now? So O-minimality is something that comes from two sources. Well, one is Grothendieck's work on so-called, what he called tame topologies. And the other is the work of logicians, notably Andrei, who who defined O-minimality, in fact. They are exactly more or less the same things. So growth index tame topologies and what we call sets definable in O-minimal structure are the same things. Well, the good thing about it is, so to use these notions, you don't need to know anything about model theory. It can all be defined set theoretically. So briefly, a structure. Well, first of all, these are subsets of real numbers of r to the power k. And this is quite remarkable because in Diophantine geometry, you usually work either with complex numbers or p-adics. Real numbers are not really usually used, but here, yes. And it's important real numbers because you use inequalities. So so a structure is simply a collection of subsets of r to the power k for k varying from 0 to infinity. Satisfying, so these subsets satisfy natural properties, so stable by finite unions. So Sk is a collection of subsets of Rk, which is stable by finite unions, finite intersections, complement direct products, and projections. And you also want each Sk to contain all semi-algebraic sets. So semi-algebraic means that this is something defined by polynomial equations. You see, if you take x squared plus y squared equals y squared smaller than 1, for example, this will be semi-algebraic. So you want all semi-algebraic sets to belong to this Sk. So this is structure. Of course, it's not very meaningful because you can take Sk to be all subsets of Rk, and you get a structure, but you can't do anything with it. So this is where, so a set is set, well, terminology, a set is called definable in a structure if it belongs to Sk. As I said, so far you haven't really defined anything. So this is where O-minimality comes in, and the easiest way to state what a structure, what is meant by O-minimal for a structure is to say that the each of the sets in Sk has finitely many connected components, and this is a very, very strong property. For example, already it tells you that sets like the graph of, say, sine function will not be definable. We take something like this, y equals sine of x. Well, this is not definable because if you intersect with the line y equals 0, which is definable, it's semi-algebraic, it's algebraic, well, you get infinitely many points. And this is how, in fact, you prove that something is not definable. So this is a strong condition. And usually it's not easy to prove that a structure is O-minimal. If you take Sk to be all semi-algebraic sets, well, this is O-minimal. Here, in fact, to prove that its structure is not entirely trivial because you need to prove that a projection of semi-algebraic set is semi-algebraic, and what's the theorem of task-cube. They are larger, so this one is not very useful either. So if you want to get something useful, you add, for example, the graph of the real exponential. So you look at equations, polynomials in exponential function. And this is O-minimal, it's a big theorem. I will manage to state, maybe in Oxford. You can also add, and this is useful, as I said, graph of sine of x is not definable. But if you restrict it to a compact interval, it will become definable in some O-minimal structure. And if you look at all functions like this, called restricted analytic functions, you get an O-minimal structure Rn. And then you can combine it with the exponential. So this one is the one we use in fact. you get this. So these are sets defined by these restricted analytic functions, also exponential, real exponential, and all semi-algebraic. So this one is rich enough for our purposes. Yeah, a function is definable if its graph is definable. Now, yes, so why they are important is because Piller and Wilke proved the theorem on counting points. So in fact, you can count rational points on definable sets. So you have a set X. We assume that it's definable to subset of A. Okay. So rational points are simply at the intersections with this one. What I mean by rational points. Well, here I stated it over Q bar, but you can also take Q bar points in there, and so you use the height, well, the usual height, which is this one, and of course there are finitely many points of bounded height up to height t, and you want to study this function. And I copy here. And what they prove is that if you have a semi-algebraic set, this may have a lot of rational points. So if you count rational points on a semi-algebraic set up to height, say t, you often get something polynomial in t. So this is not good. But what they show is that if you take a set definable in a O-minimal structure, and you remove its algebraic part, which is the union of all positive dimensional semi-algebraic subsets, and on this set there are very few rational points. In fact, it's for any epsilon. Well, what I stated here, I stated it for all number fields. It's also uniform in the degree of a number field, but basically the function, the number of rational points outside of the algebraic set, algebraic part of a definable set, this number is like for any epsilon a constant depending on epsilon n to the power epsilon. So very small, it's sub-polynomial if you like. And this is what you need. And of course, they also prove a statement over Q bar, and they prove that this counting function, this estimate, is uniform in the degree of numbers here. So and this is useful and very important in Diophantine applications. Like you have this, for example, for all quadratic fields. And there's a lot of course, the question is whether you can improve these. For example, replace this n epsilon by log n, or say something about this constant. So for example, is it polynomial in D? And there's a huge amount of activity now and great progress on this by people in Warwick and Manchester, and also in Israel. So, and actually, there's a very strong version of this theorem, which is used in the proof of the Andrei conjecture I will mention later. So this is the accounting statement. Now I want to explain how this strategy works, and I will give you the simplest, non-trivial example of a kind of problems we look at. So let's look at the exponential function. Exponential uniformized by 2 pi. And it's important because what you want rational point to go to roots of unity. So you want them. In fact, there's a statement in transcendence theory saying that if you look at this exponential function, the points in Q bar upstairs, which go to Q bar points downstairs, are precisely in rational points here. And if you didn't, So bi-algebraic points are exactly rational points upstairs. But if you didn't take 2 pi I here, then in fact the only rational point, bi-rational point, would have been 0. That's a theorem of Lindemann. Okay, so the question is, so we take an algebraic curve in C star cross C star, so we view it as an algebraic, right? It's an algebraic variety, it's an algebraic group, defined over Q, by the way. And we assume that Z contains infinitely many points of the form, well, whose coordinates are roots of unity. Or as I said before, precisely the bi-algebraic points. So we call such points special because they are special. So what can you say about Z? So Z is a curve in C star cross C star, which intersects infinitely many special points whose coordinates are roots of unity. And the answer is yes. In fact, Z is a translator of a subgroup. So you can state it either geometrically, so it's an image of a rational affine subspace here in C cross C, or you can write its equation, so polynomial, and it should be of the form, this form, equals the root of unity, or this one. And these are equations of translates of a subgroup, and of C star cross C star, and by a root of unity by zeta. It's a Diophantine question, because what really it tells you is that if you have a polynomial which is 0 in two variables, which is 0 on infinitely many roots of unity, then it's of this shape. Okay, so it's a Diophantine question. This was first asked by Serge Lang. You can find it in the latest edition of his book Algebra. So yes, I said the point is called special if it's a root of unity. So a variety of this form is translated of a subgroup is called special, and the theorem is an algebraic curve in C star squared containing infinitely many special points should be special. It's also sometimes called multiplicative Manin-Mumford. You can generalize it to higher dimensions. So if you have a subvariety of C star n with a dense set of special points, it should be special. And so I want to show you how Piller-Wilke strategy is used on this. So first of all, you identify topologically C with R2. And you look at the fundamental set for the action of, so C star is a quotient of C by Z. And you look at the fundamental set, which is for the action, so this is that. For the action of Z on C. So pi is the quotient of F cross F by Z cross Z. And you look at the pre-image. So why you're doing it, why you look at the fundamental domain, and this is because you want the map pi to be definable in some O-minimal structure. The map pi on C cross C is not definable in any O-minimal structure, for pretty much for the same reason as the graph of sine of x is not definable. But if you restrict to F cross F, then it becomes definable pi. And the preimage of our curve Z, which I call curly Z here, is definable in the structure R and X. It's not hard to prove. If you write down pi restricted to F, you see it. You see the real exponential, and you see a restricted analytic function. Yeah. So that's one ingredient, because you will want to apply Piller-Wilke theorem to the Z here. Sorry. Yes. And the second very important ingredient is the degree as an algebraic point of a special point. Well, special point is root of unity. It has an order. The degree of the root of unity is phi Euler phi function of this order. And you can, for example, take a coarse estimate is bigger than the order to power 1/2. Phi of n is bigger than n to the power 1/2. So you have this estimate. So the Galois degree of special points grows like, say, square root of n. Then you want.
Sorry, what is C of n?
It's a constant that depends on n, something. I didn't want to. Oh, sorry, it shouldn't be n. It should be, of course. Sorry, there's a typo here. This n shouldn't be there. N is it's some number c, which is absolute. No, this is very important. So there's no n here. It's a typo. It shouldn't be there. And well, pre-special points, so pre-images of special points in F cross F are exactly rational points. And it's really not hard to see. So you see the first coordinate F is 0, 1 cross R. Well, it's not hard to see that their height is bounded by n. You write down what it means and what the order means and what. So we have these two estimates. Yes, it's very important. I repeat that n shouldn't be here. And then, the last thing you need is the bialgebraic characterization. So this is a kind of functional transcendence result, which says that Z is special. So Z is a translator of a subgroup. If and only if this curly Z contains a positive dimensional semi-algebraic set. Again, it's not hard to prove, and so we have these 4 ingredients here, and in much more complicated cases, the Andrei conjecture, you have the same ingredients, but they're much harder to prove. Especially this one, the Galois degree. That's the hardest one. Okay, so now how do we put them together? So by the third ingredient, this is what we're going to use. We're going to use this characterization. We want to show that Z, curly Z contains something semi-algebraic. And so we apply Piller-Wilke to this. So we have this algebraic part. This should be a curly Z. I'm sorry again. This is not Z, it's curly Z. If you remove algebraic part, it contains for example, n to the power 1/4 points, rational points up to height n. This is what Piller-Wilke tells you. You take epsilon equals 1/4. You can also assume Z defined over Q. It doesn't make any difference. It's defined over Q bar because it has infinitely many Q bar points, and you can take the conjugates if you want. Now, so the Galois orbit of Z by this ingredient here. It lifts 2 points up to height n, of course, because the Galois action doesn't change the order naturally. And so that gives you n to the power 1/2 points. But if you put this inequality and this one together, you see that most rational points should be on a semi-algebraic part, which has to be positive dimensional. And you finish by this. So this is the strategy that Piller and Zanya first applied to Mannion-Mumford for abelian varieties. And it works in the same way in much more complicated cases, such as Shimura varieties. 5 minutes? 10 minutes. Okay. So now this is the first really baby case of the sort of questions we look at. Kind of still difficult type of questions. So let me show you an example of a Shimura variety now. So that was multiplicative Mannion-Mumford. So now let me say something about what is called Andrei conjecture. Again, in the first simplest example. So the first example is of a Shimura variety. Positive dimensional Shimura variety is simply the moduli space of elliptic curves over complex numbers. So it's a quotient, analytically quotient of upper half plane by itself to Z. And of course, you attach an elliptic curve to an element of H by taking this torus C mod Z plus tau Z. So there's a J function, which is analytic function, and that established an analytic isomorphism between H mod SL2 Z and C. And now here you want to call a point special. Again, you can take the characterization we had before. You can take it by algebraic points. So points which are algebraic here, so tau in H, that go to algebraic points here. And it's a theorem in transcendence that these points are precisely quadratic points on H, imaginary quadratic. Previously, we had rational numbers, and here we have imaginary quadratic points. So this elliptic curve has a geometric attached to a special point, has a geometric property that it has what is called complex multiplication. So there are more endomorphisms than just multiplication by integers. It's called a CM elliptic curve. So these are special points. These things, J of tau for tau imaginary quadratic, are also sometimes called singular moduli. That's the same. So as I said, a point is bialgebraic for the J function if and only if it's a CM elliptic curve, even only if special. Now you also have special subvarieties. So now we look at C cross C. View C as a J line, by what we said before. And special subvarieties are, well, either you have fibers over special points, C cross a point, special and special point cross C, but others are the modular curves Y0 of n that parameterize pairs of elliptic curves with a cyclic isogeny of degree n between them. You can describe it analytically as H mod gamma 0 of n. So these are integer matrices of determinant 1, where the 0 mod n in the lower left corner. Or in fact, you can describe them by a polynomial. Like we said, we have these polynomials in the previous case. So for this one, for y0 of n, you also have a polynomial that's more complicated. Modular polynomial of special kind, which is well studied. So the first non-trivial case of the Andrei conjecture is the question analogous to what we had before. So we have an irreducible algebraic curve in C cross C. We assume that projections are dominant. Well, if they are not, then there's nothing really to prove. And you assume that Z contains infinitely many special points, then it should be the modular curve Y0 of n. So this statement, in fact, is not trivial. And the first proof was given by Andrei using results in Diophantine approximation on the J function. So his proof is unconditional, but it doesn't generalize at all to anything, not even to higher dimension products of C to the power n. It was proven by Basedix-Hoven under the assumption of GRH. So that's generalized Riemann hypothesis for imaginary quadratic fields. So he uses the effective Chebotarev theorem. And this proof does generalize, and it was generalized 15 years ago by Wilmot, and myself to the general case of the Andrei conjecture. And then by Jonathan Peeler in 2008 using O-minimality. And so yes, as I said, Peeler's strategy applies here too. You do exactly this Peeler's proof. You do exactly the same things. So let's go back to this. So the pi function now is J cross J, right? So the fundamental domain is the usual fundamental domain for the action of SL2Z on, this thing here on upper half plane. Again, pi is j cross j, pi minus 1 of z is definable. It's not hard to prove. Galois degree of special points, well, this is well known. So what replaces the order here is the in fact is a discriminant, absolute value of the discriminant of the endomorphism ring of SCM elliptic curve, which is an imaginary quadratic field. When you have an infinite set of special points, SCM elliptic curves, it goes to infinity. And the estimate is also so is known to be also discriminant, something like discriminant about 1/2, maybe 1/2 minus epsilon, but it's a small power of discriminant. But this in fact in general for general Shimura varieties is the hardest part to prove. Height of 3 special points, so this is also not hard to work out. It will be something like it will be like d tau also to some power. And then the rest. So you have this bialgebraic characterization, and the rest goes formally the same way. Wilkie shows that curly Z has a positive dimensional algebraic part, and you conclude. So I don't really have time to go into Shimura varieties in general. So very briefly, there are higher dimensional analogs of this, although there are curves which are Shimura varieties which are different from this one. So you see this H is what is called Hermitian symmetric domain. And there is a theory of higher dimensional Hermitian symmetric domains. So this is a what is called congruence arithmetic subgroup of SL2Q here. And a general Shimura variety is a quotient of such domain by an arithmetic subgroup of a certain algebraic group of Q. And the most important example that really does come up a lot, it plays a crucial role, for example, in Falsing's first proof of Modell's conjecture, is the moduli space of principally polarized abelian varieties. It's a direct higher dimensional generalization of S mod H mod SL2Z. So here the group is a symplectic group. H plus is what is called Siegel half space. We have this uniformization map pi, which is an analytic map, highly transcendental. So special subvarieties are a bit harder to define, but they will be subvarieties of the same kind. Also quotients of X plus mod gamma for some subgroup of G. So you can describe them precisely. You can describe them in terms of differential geometry. So they are weakly special. So they are special points which correspond, well, in case of AG, like in the case of moduli of elliptic curves, they correspond to a complex multiplication of abelian varieties. So those who have a maximal number of maximal ring of endomorphisms in a certain way. So you can also characterize special subvarieties as loci of abelian varieties with additional structure. For example, a endomorphism ring of a certain type, but not only. And the Andrei conjecture is a statement exactly as before. So S Shimura variety, Z subvariety containing a dense set of special points, then Z is special. And so I'll briefly, so this, so far the main achievement of this O-minimal strategy was a complete proof of this. And it's been open for 35 years. So it's and many people worked on it using different methods. Results, so we proved with Benoît Klingler and Emmanuel Ulmont that GRH implies Andrei. So this combines Galois theoretic techniques with equidistribution, and GRH is used twice, and once maybe it could have been avoided, but the second time, no, with this sort of strategy. So it really relies on generalized Riemann hypothesis very, very heavily. Equidistribution, on the other hand, wasn't needed really, as was shown by my student Chris Daw, who's at University of Reading now, in the status 10 years ago. So, and now, I mean, the only hope to prove this conjecture unconditionally was by using Pila-Zania strategy, O-minimality. So here there are a lot of results. So I already mentioned that Pila did it first for C2, well, the case I explained. Then for C to R, then with Jacob Zimmerman, he proved it for A2, which is AG for modular space of principally polarized abelian surfaces. Then for AG up to G equals 6. So why? So as I said, the hardest part is to prove lower bounds for Galois orbits without GRH. Under GRH, it's not hard to do, but without GRH, it's very hard. So it was known until quite recently for G small or equal to 6. Then Zimmerman used a very, very hard result on the so-called average Colmes conjecture, which a priori has nothing to do with Andrei conjecture. It's a formula for an average of Falting's heights for CM abelian varieties. That was proven by two groups of people quite recently, 2015 maybe. And Zimmerman deduced lower bounds for special points for AG from it, and from Massa Wusthal's result in transcendence. And then it was proved in maximal generality, in full generality in 2022, but this should be attributed to a large number of people. Well, it really is a combined effort. Even though formally it's attributed to Pila, Zimmerman, and Shankar. What's interesting, so here, as I said, the last stumbling block was lower bounds for Galois orbits. And we used another, a strong, I said that this Pila-Wilkie theorem, there are stronger, much stronger statements now, namely one due to Gal Benyamini, who is in Israel. And we adapted it, we used it to prove lower bounds for Galois orbits. But there was one ingredient missing, an upper bound on height, and that was done by Zimmerman and his co-authors. So I just want to say, yes, there's a, so this side, there's a far-reaching generalization of Andrei model Lang, but it's really much more general, called Zilber-Pink conjecture, which concerns the atypical intersections of a variety with special subvarieties. So if you like, two curves in C3 normally don't intersect. If they do, then the point of intersection is called atypical. That's what it is. So and it's conjectured that if a variety intersects atypically many special subvarieties, then it should be contained in a special subvariety. So this is Zilber-Pink conjecture, which is largely open, but there's a good progress on this. So I cite some people, I certainly, so it started, I think Bombieri was the first one to formulate such questions, maybe before C started LN a long time ago, but so here I cite a number of people who worked on it or are working on it, but there are many more, I'm sure. So yeah.
One question for Andrei.